Have you ever encountered a situation in your embedded C programming where a variable of one type simply wouldn't fit into a function or operation expecting another, even though logically it seemed like it should? Imagine trying to put a square peg in a round hole, not because it's impossible, but because the system is designed for a specific shape. This common challenge is precisely where a powerful technique comes into play, allowing you to explicitly guide the compiler. In embedded C programming, typecasting is the process of converting a variable or value from one data type to another. It is an explicit instruction to the compiler to treat a piece of data as if it were of a different type, enabling operations or assignments that would otherwise result in a type mismatch error or an implicit conversion with unintended consequences. This explicit conversion is crucial for managing memory, interacting with hardware registers, and ensuring precise data handling in resource-constrained environments. The fundamental why behind typecasting lies in C's strong typing system, combined with the need for low-level memory manipulation in embedded systems. Different data types occupy different amounts of memory and have distinct interpretations of their bit patterns. For instance, an 8-bit integer and an 8-bit character both use 8 bits, but the compiler interprets them numerically for the integer and as an ASCII character for the character. Typecasting lets you override the compiler's default interpretation, providing precise control over how data is handled at the bit level without altering the actual bit pattern itself. It is about instructing the compiler on how to view the data. To effectively use typecasting, you explicitly place the desired data type in parentheses before the variable or expression you wish to convert. For example, if you have an integer variable named value and you need to pass it to a function that expects a floating point number, you would write float in parentheses before value like this. Float value. This temporarily converts value for that specific operation. This is particularly useful when performing arithmetic operations, where you need to force floating point division instead of integer division, such as calculating averages from integer sensor readings, or when interfacing with hardware registers that might be defined as generic pointers. An interesting nuance in embedded systems is the distinction between static and reinterpreting casts, although C typically does not formalize these terms as C++ does. A static cast generally implies a conversion where the compiler understands how to transform the value, like converting an integer to a float. A reinterpreting cast, often seen with void pointers or when casting between unrelated pointer types, instructs the compiler to simply treat the existing bit pattern as a different type, without attempting a value transformation. Understanding when you are converting a value versus merely reinterpreting bits is vital to avoid unexpected behavior, especially when working with memory-mapped peripherals. Ultimately, mastering typecasting provides embedded C programmers with a critical tool for robust and efficient code. By allowing you to precisely control how data types interact and how values are interpreted, you gain the ability to manage memory efficiently, optimize arithmetic for performance or accuracy, and interface seamlessly with diverse hardware components. This explicit control not only prevents subtle bugs arising from implicit conversions, but also empowers you to write highly optimized, predictable, and reliable code essential for embedded system design.